Imagine a square with sides 1 meter long. The diagonal of the square is square root of 2 by Pythagoras' theorem, but what exactly is the length? Well, we can attempt to measure it, but you see we'll never arrive at a final value, because this is the irrationality of the square root of 2. How can a never-ending decimal number represent a finite length? Or how does irrationality lead to paradoxes? Even better, can we prove that the square root of 2 is irrational? So here's my guide to irrationality in math. Let's attempt to answer the first question. If you to construct a table of square root of 2, you know where to start but not where to end. To understand this, we have to understand Zeno's paradox. Zeno's paradox says, imagine 2 points A and B. First you move half of AB, then another half of the remaining half, and so on and so forth. It continues in an infinite series that looks like this. Therefore, the distance must be infinite, as it will continue to divide by half infinitely, meaning we'll never reach our destination B. But we know that is not true, otherwise motion would be impossible. So there must be one false assumption Zeno made, which is an infinite sequence means infinity. As you continue to divide the remaining distances, the denominator increases. It will continue to increase to infinity. 1 divided by infinity, although unconventional, is 0. Therefore the sequence will come to an end. This brings about the idea of limits and boundaries. In the case of the square root of 2, the square root of 2 is always between the boundaries of 1.4 and 1.5. If we move further to the second decimal number of the square root of 2, the answer lies between 1.41 and 1.42. The square root of 2 will never exceed the value due to the boundaries always in between. So therefore we are able to represent a finite distance of a never-ending decimal, because a never-ending decimal refers to an infinity within a given boundary. But you'll never be able to create the table with 100% accuracy, because the decimals increase to an infinity despite it remaining within a boundary. So how do we prove that the square root of 2 is irrational? An even number is any integer multiplied by 2. Take 2a as an even number. Squaring this gives you 2a squared. So if you square an even number, you end up with an even number. An odd number is any integer multiplied by 2 plus 1. If you take 2a plus 1 as an odd number, squaring this gives you 2 in brackets 2a squared plus 2a plus 1. So squaring an odd number gives an odd number. Now let's assume the square root of 2 is rational. Squaring both sides gives 2 is equal to a squared divided by b squared. So a squared is equal to 2b squared. If a squared is even, a must be even. So a could be represented by 2x. If we replace this in our equation 1, 2x squared is equal to b squared. If b squared is an even number, b must be even. So both a and b are even. An irrational number can be represented as a ratio between two numbers that share only one factor, which is 1, making them co-prime. But if a is even and b is even, a divided by b will always share a common factor of 2 and 1, and so it cannot be rational